Well, a warm welcome indeed to anyone joining. Go ahead and get yourselves ready. Really prepare yourself. Grab a notebook, grab a pencil or a pen if you're so bold. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a most challenging problem. Intended for pre-calculus students, but an Algebra 2 student could do this, and certainly someone going into calculus should be able to do this, but it will be challenging. I'm not gonna sugarcoat it. The title of this video is called Inverse Identity Crisis, and that's because finding the inverse of this is not easy. It could be a bit of a crisis. As you can see, we have just a function. That's all. And the goal is ultimately to find the inverse of this function. So we're going to have to do a couple of things to consider carefully how to work with this, because we have a linear piece plus some kind of radical expression. And in order to do this, we're first going to take a look at the domain of the function, and then consider the domain of the inverse. If you're not incredibly familiar with domain, go ahead and check out my video on domain. We covered three main types of restrictions, three main types of functions rather that have domain restrictions, and sort of how to deal with them. And then for part B, the meat and potatoes, the really challenging part is going to be to find the inverse function. As a bonus, which I'm not going to work with you here, but I encourage you to try, is to verify that your inverses are valid with composition. So what that means is if we have f of x and f inverse, if those are truly inverses of each other, then we should be able to plug the inverse into the original function, composition that's called, and get x. Similarly, we should also be able to take the inverse of the function, plug the original function into that inverse, and also get x. So that's something I encourage you to do on your own if you can hang and find the inverse. You can give yourself about, maybe 12-15 minutes to try to do this problem. I'm not sure exactly how long it will take, but however long it takes you is fine. All right, without further ado, let's get started here. So this linear piece doesn't have any restrictions. I can plug in any value of x and there would be no problem. You just multiply by 3. However, this portion inside of an even radical cannot be negative. We're not allowed to take a square root of a negative. That produces I and all these other weird things that we're not focusing on here. So we just need 4 minus x to be either greater than 0 or equal to 0, which is literally the opposite of saying that it's negative. We need it to not be negative. Therefore, I just say 4 minus x greater than or equal to 0. So 4 needs to be greater than or equal to x. You might not be perfectly comfortable with seeing it like that. Maybe you're more used to seeing it like that. You should know that these are the exact same, but maybe due to the way that you're normally seeing these domains, might not be obvious right away that those are the same. So understand that those are exactly the same. X needs to be less than or equal to 4. Well, then what happens at x equals 4? It says that it can be equals to 4, so let's see what happens at 4. Well, that's simply going to be 3 times 4 plus the square root of 4 minus 4. And so the radical portion kind of goes away, becomes 0, and so we can say that f of 4 simply equals 12. But x needs to be less than or equal to 4, and you'll notice that if we make x smaller, this 3x portion will be smaller. For example, if I use a smaller value of x, remember I cannot use a bigger value of x, that is not in the domain. 4 is sort of like at the cusp. We can plug in anything from negative infinity to 4. Like f of 3, for example, this would be 3 times 3 plus the square root of 4 minus 3, which is 9 plus square root of 1. 9 plus 1 is just 10. So you'll see that it's decreasing if x is decreasing. That makes sense, right? If I say 3 times a number, it gets smaller as the number gets smaller. So why is that important? Well, because it seems that we have this trend of going downwards. If x is getting smaller, then the function value is getting smaller. And that's important because the range or the outputs of this original function is going to determine the domain of the inverse function. So the domain of f inverse is going to go from negative infinity to 12, but the original function allows inputs from negative infinity all the way to 4. Okay, so we've interpreted the domain. But that's not even the hard part, guys. Now it's time to do the truly difficult portion, which is to find the inverse function. It's pretty common for us to, let's write this out, y equals 3x plus square root of 4 minus x. It's pretty common to simply exchange the x and y, swap them, switch them. So we're going to have something that says like x equals 3y plus the square root of 4 minus y. And that looks tough to solve. We want to get the y's all together so that we can have just a single y expression. And remember that the y here, this really just stands for f inverse. It's like our new output, our new y. We want to try to get that. But this equation is a radical equation, and you should be familiar with how to solve radical equations. We need to get the radical portion by itself, that way we can cancel the radical. So I'm going to subtract 3y on both sides. And now we're able to get rid of this radical by squaring both sides. So square both sides carefully. That's going to give you x squared minus 3xy minus another 3xy, we call it minus 6xy. And then plus 3y times itself, 3y times 3y is 9y squared. And on the right side, we nicely break the radical. So this looks a little bit messy, doesn't it? It is a quadratic, but we have to be aware that it's actually a quadratic in y. This is not a quadratic in x. This is called a quadratic in y. Since we want to solve the y, we're going to have to identify that we have a squared on the y, and then we have these terms that are just y, and then we have some constant terms. I know x squared doesn't seem like a constant, but these are treated as constant terms because it's not a y. So let's move everything over. That way we can get the following format for the quadratic equation. We want ay squared plus by plus some c equals to 0. This is the standard form of a quadratic, and we know how to solve those. We can either factor them, which I don't think is really going to be the recommended method for this, or we can simply use the quadratic equation. That's probably going to be how we approach this. Let's first just get everything on one side and see what that comes out to be. Now I'm going to start off with 9y squared in the front because that's my ay squared term. But then notice that I'm going to add the y over here. So I'm going to have minus 6xy and plus y. Those terms both have y, so they're kind of like the by term. And then I'm also going to have to subtract the 4 over. So I'm going to end up with x squared and minus 4, right? The x squared here and the 4 that I subtracted here. Finally, everything's on one side. And we can kind of condense things a little bit. Here we need to have just a y term. So what would be left there? Well, I'm going to call this 1 times y, and I'm going to call this negative 6x times y. So if I put them together as a y term, we have 1 minus 6x times y. And then our quote constant term, x squared minus 4, is right there. Okay, so this is like our a, this is like our b, this is like our c. As I mentioned earlier, we're probably not going to try to factor this with typical factoring methods. It's possible that it does. Who knows? I'm not trying to sit around and find out. It's safer to just use the quadratic equation, which you might have some kind of sing-song or rhyming method, or however it is that you remember the quadratic equation. But this time we're doing it in terms of y. So instead of x equals, let's go ahead and write it out just to make sure you're comfortable with this. Negative b plus or minus the b squared minus 4 times a times c all over 2 times the a. Yeah, that's going to be our solution, or rather our two potential solutions. And let's go ahead and fit that in. So we're going to have negative 1 minus 6x plus or minus, oh boy, here we go, 1 minus 6x squared minus 4 times the a value of 9 times the c, which is x squared minus 4. This is looking rather messy, guys. Over 2 times a, which is 9. All right, easy things first. Let's work from left to right. We can distribute the negative sign. That much we know, right? This might look complicated, but don't forget the basics. You can distribute the negative here. So we have 6x minus 1 plus or minus. Let's FOIL this. This is going to be 1 times 1, negative 6x, and another negative 6x. And then we're going to have negative 6x times itself. So negative 6x times negative 6x gives us plus 36x squared. Have no fear, because this is going to be minus 36 times x squared minus 4. So some stuff's going to work out kind of nicely, it looks like, over 18. Okay, we're trucking on through. This is not too bad. We have 6x minus 1 plus or minus. Well, let's see what happens here. 1 minus 12x plus 36x squared. But then we're going to subtract 36x squared. Thank goodness, that makes things a lot easier. Plus 144. Okay, all over 18. So the nice thing here is that these giant x squared terms cancel out completely. And we end up with 6x minus 1 plus or minus square root of 1 minus 12x plus 144 all over 18. Interesting. The question is, are we going to use plus or are we going to use minus? Well, here's something that we need to keep in mind here. Of course, we can only use one of them. What we need to keep in mind is we need to keep in mind the domain of the inverse. The inverse needs to be less than 12. Anything less than 12. So let's see what happens if we plug in something which is less than 12, right? Let's see what happens when x equals 12. Then our inverse would be 6x, would be 6 times 12 minus 1 plus or minus the square root of 1 minus 12 times 12 plus 144. See how nicely that worked out, wowza. All over 18. So negative 144 plus 144, that's kind of nice. We end up with 6 times 12 minus 1, and here's the kicker. Plus or minus, we're trying to figure out which one it is. Plus or minus the square root of 1 all over 18. What does this need to equal to? Well, if x equals 12 on the inverse, then that means y equals 12 on the original function. We took a look at that. It had a value of 4. So whichever one we're going to pick, it better come out to be 4. Let's see here. We're going to have 72 minus 1 plus 1 over 18. Or we're going to have 72 minus 1 minus 1 over 18. Which one is correct? Is it going to be the plus? Is it going to be the minus? Well, if I do this, of course, those just cancel. We get 72 over 18. And if I subtract 2 from here, I get 70 over 18. This is not going to give us 4. This one is going to give us 4. So that reveals to us which is the correct expression, I guess you can say, to use for our inverse function. We're going to be using the positive root. So we get that the f inverse of x is 6x minus 1 plus the square root of 1 minus 12x plus 144 all over 18. And that is our inverse function. Amazing. Now, as I said earlier, it's a challenge for you to verify that our inverse is valid by using composition. So what I want you to try to do is I want you to verify that f of f inverse is just going to get us back to x, I also want you to verify the tougher one, that f inverse of f of x equals x. I have to say this is going to be the tougher one of the two. I'll leave that as an exercise for you guys. I also encourage you to graph both the function and the inverse function, remembering that we have some domain restrictions. If you keep that in mind and get a good understanding of what it looks like visually, I think it'll help in analyzing these functions as well as their inverses. Okay, that's enough blab out of me. I hope you learned something from this example, and I hope you were challenged by this example, more importantly. I'll see you guys next time.